Now at this point, the next step is going to be for us to add a bit of collisions. Some of the sparks should bounce off the surface of Iron Man, and it's going to be happening really fast. But we'll add that to our system just in case. The way we're going to be adding this is we're going to get the geometry here. I'm going to do the operations here. We could do them somewhere else, but I think it's going to be easier for us to have everything on the same place. So here on the object, this is another object merge, and I'm just going to get Iron Man. We'll go to Iron Man, out Iron Man Geo, and we'll have this here. Let me hide everything else. Now, we've seen before that we're going to be using this as a static object, and it's going to be a deforming static object, meaning that the points are changing, the object is actually changing shape. It's not just that it's an object that's being transformed in rotation, on position, or scale. It actually has some deformation happening. So the way we're going to do that is we're going to try to simplify this, because it can be kind of calculation intensive. It's not going to be too hard because we don't have that many particles, but just so we can make things faster, go faster here. One thing we can do is we can actually delete some of the parts of Iron Man. It's not only we're not going to be looking at the legs, for instance, but considering the lifespan of the sparks, they're not going to get that far. So I'm going to delete the legs. I'm going to zoom out. I'll select type S, and I'll select, we can select by groups. We can select by 3D connected geometry, but let's check out the groups that we have, geometry groups. Maybe we have, of course, now this is great. So we have a group for the boot. We have, I'm going to hold shift, grab this boot. I'll grab this part of the leg, this part of the leg. We have something else going on here, which is the inside. I'm going to delete that as well. Not going to be visible. It's going to be visible, but it's not going to interfere with the collision, so that's fine. And I think we can get away with this. Let's just hit delete. And as you can see already, we're deleting all those extra pieces that we didn't really need. We could go further with this. We could delete fingers and all that stuff, but I think this is already going to save us a good amount of calculation. Okay, so now we have the animation, but we don't have to deal with the legs. So the next step is, we know that this, let's change this to, let's create a null here, and we'll say this is out Iron Man collision. So we want to collide with this, but we know the calculations in particles will be happening based on a volume. But let's test this out. So we have Iron Man collision, and this is what we're going to be. Let's connect this to the second input. Let's go here to our particles, and let's make sure we create our static object. And we'll merge the static object into our system. Remember that we want the static object to be to have a collision relationship, and left influences right. Okay, left inputs affect right with a collide relationship, and this is what's going to be coming in here on our static object. We can choose swap path. We'll actually refer to it here, out Iron Man collision, accept. And we have to turn on this option, use deforming geometry, otherwise it won't be animated. Okay, use deforming geometry, and that way it will be animated. Let's have a look at how the collisions are being treated here. Let's go to the collisions, and here on the collisions, we'll disable the display geometry, and let's have a look at the collision guide. So this is what's actually being used for calculating the collisions. Let me hit Shift W to see the wireframe. You can see this is extremely low res. We do have some weird stuff going on here, but yeah, this is very low res. It's pretty fast, but it's not going to be accurate enough. the sparks are going all over the place, and it's going to be hard for this to actually be able to detect it. So what we can do is here we could increase the uniform divisions. We could say instead of max axis, we can actually say by size and establish a size for each voxel of this volume, 0.05, 0.01. 0.01 already takes a lot longer to calculate. As you can see, we are getting some weird stuff here. Yeah, and this takes a lot longer. Let's get away from this. Let's not use this. So what I'm going to do is let's see what we can do to solve this. So I'm going to disable this, and let's go display geometry, and let's go up. Okay, so what we can do is we can calculate our own VDB. We can even cache it and feed that into our POP network. So let's try and do that. So the way we convert geometry to VDBs is by using VDB from polygons. VDB is just one format for volumes. It's more optimized. It's a scarce volume format, meaning that it will only store data where there's actually something to store, and everything else is going to be empty, instead of grabbing the whole a whole area where not much is happening, just something in the middle. So VDB will be more optimized and faster. We'll talk about that in more in depth later on, but for now let's just have a look at what this gives us. As you can see, this is the area that's being considered, but we only have data on that area. So this is all going to be empty, and it's going to be much faster than a regular volume, which would have data everywhere. Now, this is basically what we want. We just want to make sure that we have a bit more resolution, 0.02, 0.01. Okay, and you can see what's happening here. So the problem here is that our geometry, a lot of these pieces are hollow. They don't have thickness. One way to solve this is by using a polycap. You can use a polycap. That's going to close a few holes. It's going to give us some weird looking results, but for the purpose of helping us deal with the object, this could be a better approach. Okay, we have a better idea of the surface. We still have a few problems there, and this should work for this situation. This will probably be okay. Let's create another output here. We're not actually using the second input for anything, so let's create something here. Collision VDB. And now once we get inside here, when we go to our static object, we can say that we want to use, still using the default, use solver default, which is the volume. But instead of using mode ray intersect, we'll use a volume sample. And basically this is just going to be, we're going to be providing it the proxy volume, which is going to be the one we just created. So out Ironman collision VDB, accept. And now if we have a look at our collision guide, we'll see we'll have what we had before. So still not a great solution. This mesh isn't great for this. So in this situation, we can try and choose the alternative. So what I'm going to do is disable this, display geometry, and instead of using the default, let's use the surface collisions. And this is what's going to be used. Let's see how this works. It's not fast, but it's not drastic. In this situation, it's going to be very accurate, but it's going to take a bit longer to calculate. And we will have to take into account the physical properties of this. And so here on the physical properties, the bounce is set to 0.5. I'm going to leave these default values. On our pop object, we'll have the bounce at 1, but multiplied by the 0.5, it's not going to be, it's going to work. And again, it's going to be so fast. I don't even know if we will actually have any particles being colliding with this. If there's ever going to be a visible bounce happening, but just in case there is, we'll have the solution. There are ways of dealing with hollow geometry, but that's a bit more complicated, and we're not gonna get into that right now. So this is what we have so far. I made a flipbook for us to check how these were interacting together, the thunderbolts and the sparks. Things are looking good, and we'll continue to work on the sparks on the next lesson.